We have managed to put our finger on the key idea of independence when we have independent trials. Events which depend upon separate trials are independent, provided the trials are independent in the sense that the conjoint probability measure is obtained via a product. In other words, we have a product measure. This is at the heart of this particular understanding of independence, the reason why coin tosses successively are independent, the mathematical reason why successive throws of a die are considered independent, both in ordinary language but in a formal and deep mathematical sense. We should promptly codify all of this in a general setting. Of course, our notation will inescapably get more cumbrous, but the results are well worth the effort. We are going to be able to get, in a particular setting, independence essentially for free. And this turns out to be a key and subtle idea. So let us do this without further ado. So we are going to look at a generalization where we have a succession of trials, and let's start by looking at a finite number of trials. How many? Let us say a chance experiment where there are n individual chance-based trials. The trials need not be the result of a particular device. In fact, we could use different objects for different trials. For example, a die once, a coin next, cards third. We'd like to have a mechanism which allows us to be flexible. Accordingly, we think of the results of each of these trials and identify them by Gothic letters, A, and identify the trial number via a subscript. So Gothic A, subscript 1, tells us the possible results of trial 1. Gothic A2, trial 2. Gothic AN, the results of trial N. In full generality, identify the possible results of trial 1 first by identifying the trial number as a subscript 1, followed by the particular result, say the kth result, and identify it as an element A1k. So A1k, as k ranges over various indices, represents the collection of possible results of trial 1. We call this Gothic A1. Similarly, Gothic A2 and Gothic AN, comprised of elements A sub n, trial number, k, identifying which outcome, gives you the collection of results for trial n. Each of these trials is chance-driven. It's a discrete setting, and therefore we ascribe an atomic measure to the singleton A1k, the atom in the first trial of obtaining the kth element. We allocate a probability, a chance, P subscript 1 for the trial, and now we move the identifier of which outcome to the argument k. So P1k is the mass in trial 1 allocated to the atom A1k. K now is allowed to run over all possibilities. Of course, the P1k's have to be non-negative, and as we sum over k, P1k has to add to 1. Do the same thing for A2, A3, AN. For trial n, the space of possible outcomes is Gothic AN. The mass function we allocate to each possible outcome, each atom A, trial n, outcome k, is the probability P, subscript n for the trial, argument k, identifying which outcome we are looking at. We now have a system of independent trials. Each trial has got an alphabet of possibilities and a mass function attached to it. These mass functions individually have to be non-negative. They have to add to 1. Non-negative adds to 1. Non-negative adds to 1. We now stitch the compound experiment together by looking at all these trials en masse. The compound experiment is specified by specifying the results of each trial. Naturally enough, we identify the results of each trial as an ordered n-tuple. The first element of the n-tuple, A1, K1, represents the K1th element of trial 1. The second element, A2, K2, represents the K2th element of trial 2. The last element, AN, K sub n, represents the K sub nth element of trial n. The notation is inescapably more cumbrous. But we have many balls in the air, and we need notation which keeps track of which is which. Right? We have identified a particular element of trial 1, K1, a particular element of trial 2, K2, a particular element of trial n, Kn, and together this forms an ordered n-tuple, which tells you what the sample point of a conjoined experiment is. As K1 ranges over all possibilities, K2 ranges over all possibilities, Kn ranges over all possibilities. You allow your sample point, your n-tuple, to range over all possibilities in a space of n-tuples. This, then, is your conjoined sample space. This is obtained as a Cartesian product of Gothic A1 with Gothic A2 and so on with Gothic AN. The sample space now is a product space. And naturally, we now need a measure, and the measure we attach, and this is where the independent trials comes in, is to each atom, each n-tuple, we attach a mass, a probability, which is a product of the individual masses. So the probability attached to the n-tuple A1K1, A2K2, ANKN is a product of P1K1, P2K2, PNKN. The verification that this is a bona fide probability measure is trite. It's clearly a product of positive numbers, it's positive. It adds to 1 because its sum over all K1, K2 through Kn separates into a product of sums over K1, K2 through Kn, just as we had for the case of 2 trials. And therefore, each of those sums is 1, and the product of 1 is 1, and therefore it's properly normalized. This gives us the setting of the compound experiment, where you have a product space and now a product measure, which is given to us via the independent trials. We now need events which are determined in terms of each trial. So let us pick the jth trial for definiteness. The jth trial has results which are captured in the alphabet Gothic A sub j. Each of those results has an atomic mass captured in the values P sub j of K, K running over all possibilities. Identify in the space of possibilities for Gothic AJ a set of indices, blackboard K sub j, which represent elements of the jth trial which can trigger your event. Identify the event AJ with the occurrence of those possibilities in the jth trial. Formally then, A sub j, clearly as an event, it has to be a subset of the sample space. Therefore, it's a collection of n-tuples. But this collection of n-tuples has as its jth member an element which is from a defined set of possibilities. It's in a restricted range of possibilities, tagged elements for the jth trial. And the remaining elements are completely unfettered. Again, borrowing strongly from the intuition we had for the case of 2 trials, we will say A sub j is determined by the jth trial. All you've done is specify a set of indices, blackboard K sub j, for the jth trial. And the occurrence of any of those outcomes triggers event AJ. The remaining trials are irrelevant as far as AJ is concerned. Do this for j running from 1 through n. We now have a collection of n independent events. A1 determined by the first trial, A2 by the second trial, and so on, AN determined by the nth trial. Any events so constructed where each of the basic constituent events is determined by one underlying trial alone, separate from the others. Any such collection of independents is, without the necessity of any calculation, independent. Why? For the same reasons we saw for the case of 2 trials. The probabilities separate and multiply. There you go. In the simplest case, this is a setting that is so familiar to us and intuitive for us. A specialization of this gives us coin tosses, throws of a die, and so on. And this is perhaps the single most important subcase of the general edifice, right? And it's worth focusing on. This is the case of a repeated independent trial. In other words, I'm flipping the self-same coin again and again and again. The coin has the same alphabet, let's say Gothic A, for every trial. Or I'm throwing the same die again and again and again. The die has the same alphabet, Gothic A, for each trial. In other words, all the alphabets, Gothic A1 through Gothic AN, are all the same. There's some alphabet, Gothic A. We can now dispense with the subscripts because you just have one common alphabet. Let's just call the possible outcomes of a trial little a sub k. And k runs over a finite or possibly a countably infinite range. Okay, now the trials are repeated and independent. They're repeated in the sense that the chance conditions don't change, and therefore for each possible outcome in a trial, we allocate a mass. And that mass, for say the kth outcome ak, is, let's say, a value p of k. The p of k's have to be non-negative, have to add to 1, positivity and normalization. We now have a chance experiment trial by trial. The statistical conditions for the trial have remained the same. But of course, the trials are independent in the sense that when you stitch together a conjoint experiment, now omega is a Cartesian product of Gothic A with Gothic A n times. And naturally enough, we'll write a product of a set with itself n times as a power, Gothic A to the power n. This just represents A cross A cross A cross A n times. What is this? It's a collection of elements, of n elements, an n tuple from your alphabet. Sampling is with replacement. Oh, this is beautiful. So AK1, AK2, AK3, AKN. The results of what happens in each of the trials when you're drawing from the same alphabet again and again and again, sampling with replacement. The product space is now simple. It's clean. It's a system of n tuples. We saw this repeatedly. For example, in 3 tosses of a coin, the product space was a system of 3 heads or 3 tails, or a triple of heads and tails. Each element of the triple is drawn from the same alphabet, H and T. The location of the element in the n tuple tells you which trial we are dealing with. And that's it. A very clean and simple notation. What is the probability measure we attach here? Well, the mass function attached to any n tuple is simply a product of the individual masses of the elements of the n tuple. So in other words, if you're looking at the n tuple, k1, k2 through kn, the corresponding probability of ak1 through akn is p of k1, the mass attached to ak1, times p of k2, the mass attached to ak2, and so on, times p of kn, the mass attached to akn. Very, very clean and simple structure. In this setting, any event A1 depending only on the first outcome, any event A2 depending only on the second outcome, any event AN depending only on the nth outcome, these constitute a family of independent events. This is now a specialization, but it's a useful and practically important specialization of a general setting. A generalization in a different direction will consider not just a finite number of independent trials, but possibly a countably infinite number of independent trials. We've seen examples of this type before. Imagine, for instance, the repeated indefinite toss of a coin. Of course, this is a Gedanken experiment, a thought experiment. One couldn't possibly toss a coin on indefinitely an infinite number of times. But one could imagine this. This now results in a setting where the compound experiment is a very rich product space, a space of entire infinite sequences of trials. All that we've done here will more or less go through, though the one place where we get a technical complication is in how does one specify a probability measure. We can't simply multiply probabilities because if you multiply an infinite number of them, you get 0. We saw that this technical complication was handled by moving to continuous spaces. We won't take the time to make that particular detour now, but we will abstract out the key elements of what we've discovered now for both finite and countably infinite spaces. And we'll capture it in a slogan. In the case of a finite or even countably infinite number of repeated independent trials, the compound experiment or the product space, to which is attached a product measure by multiplying individual atomic probabilities, in such settings, events determined by distinct trials are independent. What this means is that in such settings, that formidable list of conditions required for independence, remember, all pairwise probabilities, all three-way probabilities, all quadruple all of those conditions are immediately and tritely satisfied. This turns out to be wonderfully rich and subtle. And we'll work on these next by looking at, first, a couple of examples from settings which are much more rich and interesting than the more banal, trite, simple examples we've looked at hitherto. We'll pick one example from the sphere of gambling, and we'll pick one from genetics. And with those under our belt, we'll now have come to a proper and right understanding of what this subtle and deep and central idea of independence is. With an idea of independence under our belt, we will now be properly situated to ask what happens when independence is lost, first by small amounts, then by large amounts. An understanding of independence confers upon us eventually a deeper and richer understanding of settings where we do not have independence. So we shall go on next to two rich examples of this particular framework we have put together.